Can you hear me now? Can you hear me now? Please, if somebody can let me know. They switched to
Yes,
my internet
I
went
can
out.
hear you.
Yeah, thank you. They took my internet went out. I quickly changed to another one. Sorry. Now, you present we already know. So how do you present this frequency for each of the variable? Well, you got to do the distribution, whether you are using both frequency and relative frequency. Most of the time, that's what you present. Then how do we show them? How do you present them? I just talking about how do you present how do you show the frequency? So there are two ways. It's that table. The one I've just shown is a form of frequency table. So table, and this is the commonest one. Then we can also show in graph. Can show in table, can show in graph. So now, sometimes you can show distribution. Where can you actually show distribution? But one of the way to present is so you can present in equation also. But that one, of course, unless you slot in some of those values for you to get it. But majorly table and graphical form. So we have already known that, okay, we have tabular form. The graphical form, there are two sets of graph. You can see the first one, we have pie chart and bar chart in one. You also have histogram, stem and leaf plot, burst and whisker plot, frequency polygon, cumulative frequency polygon, also called Hogarth graph. All these one, they are one. So what we mean by one is that the type of variable you are dealing with depends on which type of graph you use. Of course, any of them you can use table. You can use table. The only thing is that normally it's straightforward. You use for any variable that is discrete, or let's say categorical, or let's say discrete. You can easily use table. It's easy. But for you to use table for continuous variable or for some anything numerical, you have to range it like age now. You cannot put all the frequency. Imagine now you are dealing with 800 people. Possibly all of them will have many, even though some of them will have the same age, but you go to have out of 8, you may have up to 200 possible value or all over 100 possible value of age among them. Will you list it on the table and begin to spoon? No. So what for the categorical variable, they have limited number of possible value. So for example, sex is 2, male or female. You can easily show in the table, know how many are male, how many are female. For ethnicity, how many are Hausa, Igbo, Yoruba, other. For religion, how many are Christian, Islam, traditional. For talk of anything, if it is something that requires yes or no, how many are yes, how many are no. All those things, you can easily present categorical variable on a table, straightforward. But for you to present quantitative variable, you may have to range it. You have to range it and say, okay, this table I'm putting from age, maybe if the lowest age is maybe less than 20 to 25, 30 to 35, all 20 to 24, 25 to 29, 30 to 24, you range it. So you will see that whichever way you can use table, but for quantitative variable, you have to now convert. By the time you range quantitative variable, that range or categorize quantitative variable has become categorical. So age is different from age group. Age group is what you are saying, less than 20 to 25. That's age group. That age group is though you have derived from age, raw value of age, is actually, it has become categorical. So that is the way you can only tabulate, put quantitative variable on a frequency table. You will be able to know how many in each category. Does it make sense? But for graph, it's very easy because graph gives you the leeway to present the way they are. So the type of, of course, if you can present categorical and numerical variable on a graph, that shows that they cannot use the same type of graph because they are different. So when we are dealing with discrete here means nominal, ordinal, and numerical discrete. If you want to present them, you can use pie chart and bar chart. Why? When it is a continuous variable, we have already talked about the continuous variable. Those are the ones that have decimal, because the one you have unlimited number of possible value in between two given values. Like blood sugar, you say blood sugar between 60 and 61 can have infinite number of positive values. It can be 60.001, 60.002, 0.0094, whatever, infinite number of value in between two given values. In that situation, is continuous variable. You cannot use pie chart and bar chart to present. You use either histogram, stem and leaf, box and whisker, frequency polygon, or cumulative frequency polygon. Can you see? If you remember, was it yesterday when we were talking about, yesterday, day before yesterday, the last lecture, when we were talking of the basic concept, when we were categorizing, we were talking about the category and the categorizing variable and data. We talked about it. I told you the first way to categorize numerical, numerical and categorical. We say under categorical, nominal, ordinal. Under numerical, discrete and continuous. And I say that one is just a crude way of making it simple for you to conceptualize. And I said that for actually you to understand, for you to make any, to do anything that makes statistical sense, you use this alternative one that say discrete and continuous. There are two types of variable, discrete and continuous. All those categorical, all those what I call categorical, nominal, ordinal, they are still part of discrete, because the meaning of discrete means there's a distinct categories, that is manageable, distinct number of categories. So you see, the only one that the only thing is that the one that is numerical discrete, we call it numerical discrete in the sense that is discrete, but discrete, the one that has numerical value. So that's it. And I told you that that approach make more statistical sense than the first one. And I told you when we want to talk about presenting distribution, you know, presenting distribution, and I say that is where you know that one is, that is why you understand. We also, when we get to probability distribution, we're going to see that that approach make more sense, discrete and continuous. So let's move further. Now, for example, now partial, let's start with partial and bar chart. These two graphs, you see, these are the one we use for the discrete, because they have distinct category. You use them, but the way you use partial is different from the way you use partial, because partial is used exclusively for, well, for mutually exclusive. So let me say exclusively for mutually exclusive. It's for mutually exclusive variable. The meaning of mutually exclusivity is that if you belong to, if you have belong to one category, you cannot belong to the other category. That's for sex now. If you're a male, you cannot be at the same time be female. If your religion, if you are Christian, you cannot be at the same time as Muslim or traditionalist. So by the time we, okay, how many Christian, how many Muslim, how many traditionalists, when we had everything together, it gives you the total sample size. So that is mutually exclusive. That's what you use pie chart for. So you know that a pie, as you have seen it, is like a circle, and the total angle of a circle is 360. It's not more than 360. So you can, so that 360 is 100%. You cannot have frequency over 100%. So you cannot belong to two. If you belong to two categories, for example, now there are situations where you belong to two categories. If they want to know your knowledge of symptoms of malaria, you now say, okay, they can list about 5 symptoms. Fever, is it there? You may say fever is there. Symptom of malaria, you may say bitter taste, is it there? You may say it's there. Vomiting, is it there? You may say it's there. Stomach pain, is it there? You may say it's there. You see, you see loss of appetite, is it there? You say. So you see, some people may know only one, that is only fever they know. No problem. If somebody now know up to 2, up to even someone can even tell you that all the 5 I've listed, they are all symptoms. So if in that situation now, the knowledge of the symptom is not mutually exclusive, because for you, if you know that fever is there, does not preclude you from knowing that bitter taste is there. So at the end of the day, if you tick, you present your questionnaire, and somebody tick all of them, and you are entering into the computer as if it's only one you can take. So it's only maybe the first one, the one you choose for that person that you want will belong to. So you cannot present that type of thing in a pie chart. But if it's mutually exclusive for the one either yes or no, either male or female, you know, it can be 3 categories, 4 categories. If you belong to one category, you cannot belong to another category. That is mutually exclusive. That's what pie chart. The bar chart, you can use it for mutually exclusive also, but you can also now use it for the independent, the other one that is not mutually exclusive. The example I've given now. For example, now look at this. Look at the first this pie chart. Talk about whether somebody have complication of diabetes or not. So the number, the proportion that have complication 48.5, you that don't have complication 48.5, the one that have complication 51.5. Now they are mutually exclusive. Is that how you have complication or not? You cannot say you have complication, you don't have complication. No, you have complication or you don't have complication. So it's mutually exclusive. You cannot belong to one and belong to the other. So everything add up to 100%. So now look at this example from diabetes also. You say the treatment somebody is receiving for diabetes. So we try to combine exercise and diet. Somebody maybe is only exercise and diet they prescribe for that person. There are some people it's only oral hypoglycemic agent they prescribe. Some people it's only insulin they prescribe. Some people they may have more than one. Someone can they can prescribe both exercise and diet plus oral hypoglycemic agent. So oral for the people that are not medical people, oral hypoglycemic agent is the blood is a drug we give to diabetic patients to lower the blood sugar. Hypoglycemic, that is hypo mean glycemic mean sugar. So hypo mean to lower it, to make it to reduce it. So when we say oral, it's something you take orally, tablet you take to reduce blood sugar. Insulin we also know is injection. Is hypoglycemic also, but it's not oral, it's injection. So it's given as injection. So now, if somebody can even prescribe all these three for people. Somebody is oral hypoglycemic agent, it can be on insulin at the same time. And it's also, they say, oh, they make sure they restrict the person and come to die and they prescribe exercise. Can you see? So imagine when somebody have this, so it's not mutually exclusive. So, though there are some that's only one, there are some that are two, and the two can be diet plus exercise plus oral hypoglycemic agent, or diet plus exercise plus insulin, or insulin plus oral hypoglycemic. It can be any of the two, or it can be any of the person can be three. So that is why for each of them, when you now look at what percentage of the sample size are each of them, you can see diet and exercise are 39%. Oral hypoglycemic agent has 81%. Then insulin 30.8%. Even when you have 39 to 81, it's already more than 100%. If you have 30 to 81, it's more than 100%. It's only if you have diet and exercise plus insulin that it's not up to 100. But if you look, it shows that this one shows that okay, there must be some people that have more than one. Some of them will have up to three. That's why you have this figure. If you try to add all the percentages together, they will be far, far above 100. If you sometimes you can even double it. So in this situation, he is telling you that, look, this is not mutually exclusive. So the treatment modality, treatment received for diabetes is not mutually exclusive. So in that situation, we cannot present this result with pie chart. If you present the result with pie chart, what will happen is that you have removed some. At the end of the day, you see 100%. That's that there are some people that take more, all those people that take more than one, you only enter one of them. So you now present with a pie chart. So it will not show the result. Pie chart not show the result. But when you present that with pie chart. Of course, you can also present this the one that are mutually exclusive that you use pie chart for. You can use pie chart also. Doesn't really matter. So pie chart can be used for any of them. You cannot use pie chart for mutually exclusive. Now, let's now move to this histogram and these others. Histogram, you can see histogram. You see what's different between histogram and bar chart. You see that both of them they are bar. But if you look at the bar chart, there are spaces when you plot the graph. Here there are no space because of the nature. You know this one is discrete. There are distinct categories like this one. I will know that 3 categories of treatment they have given us here. See, you can see But in this one, there is no dictation because the value are continuous. A numerical value that they have decimal. So there's no sharp boundary. So because of that, that is why the graph the bar are contiguous side by side. Where one end is where the other one begins. So there's no gap. So that is why this one is presented like this. And you will also see the shape, even though we have not talked about probability distribution, you see the way it goes up and come down. Most of the time, most of the things that are continuous variable, naturally they follow that pattern. Now, we'll discuss it later. The graph go up and come down. What you see in this graph is this. Just look at it. If you look at the horizontal, look at, we are using weight for this one is for weight now. Horizontally is showing the value of the weight from left to right, 60, 70, 80, 90, 100. Then the vertical is the frequency. How many in each category? How many have each of these values? That's what they show you. You will see that as the value increases from 60 now to 70, the number, the frequency increases. That's why this thing is going up. As the thing move to 70, 75, it increases. You will see by the time another 80, close to 80, it peaks. Once it goes beyond that, 80, 81, up to 90, the frequency begins to come down. So we discussed that in normal distribution. That's the pattern of many biological and social science variables, like weight, height, many blood sugar, blood pressure in the society, IQ, all those things, behavior. If you can measure behavior, quantify it, it will go like that. Because as the value of that thing begin to go up, the number in the society that has that, the value, that particular value increases, just like weight increases until it reaches a certain age. Beyond that, the number decreases. So we will not talk much about that. When we get to probability distribution, we'll talk about number distribution. You'll be able to conceptualize it very well. Just know this guy is for continuous. Look at this, term and leaf. This term and leaf is the same thing as, it's showing the same thing as the histogram. It's only something, it's only that this one is different. It gives more information. If you look at it now, this one is just sitting, the stem and leaf is sitting on the side. So this one is sitting on the base. Histogram is sitting on the base. But the stem and leaf is sitting on the, it's just like a bottle now. Bottle that is standing on right, you put it by the side. Can you see the way it goes? Up, also come down. So it's just sitting by the side. It's the same shape. And it's the same, for this thing, it's the same data I used to plot this weight. I used to plot the two of them. It's the same data set. But the issue there is that the stem and leaf give more information than histogram. Because in the stem and leaf, if they publish the histogram, you probably in a journal, you show the histogram, yes, you can see the shape, that's all. But if you publish the stem and leaf, you also have the person, the reader, also have access to the data set. So how is it? Look at the way stem and leaf being plotted. Stem and leaf. The leaf is usually the last digit. The initial digit is the stem. Now, the last digits, that last one digit is the leaf. The initial digit is the stem. If we are dealing with a data set that has 3 digits, for example, now, when we measure our weight, height rather, usually for adult, usually 3 digits. There's no adult that will, well, unless all those with people with achondroplasia, that we have maybe anything less than 1 meter. But you see people 1 centimeter, 1.7 meter, 1.6 meter, 1.565, 1.8, or if it's a centimeter, 176, whichever, whether you measure in centimeter or you measure in meter, you have 3 digits. In that situation, the leaf will be last digit, the stem will be the first 2 digits. But in this case, it's weight. And most of the time, unless somebody that is above 100 and above, that will have 3 digits in weight, when you measure in kilogram. In that situation, even in this data set, nobody has up to 100. So there are 2 digits. So the second digit, which is the last digit, is the leaf. The first digit, which is the initial digit, is the stem. Are you seeing that? If let's say there are 3 digits now, the stem will be made of first two digits, while the last digit is the leaf. So let's look at it now. You will see this first set now, you see 2. The first column is in as frequency. For the first one, you have frequency of two. There are only two in this category, and the two are 57 and 59. Can you see the leaf? The stem here for that one is 5. The leaf are 7 and 9. It means that one person weigh 57, the other one weigh 59. The second row now, you have 7 of them. The frequency is 7. And the stem is 60. The leaf are 0, 0, 0, 2, 2, 3, 3. That is 60, 60, 60, 62, 62, 63, 63. The third one is 9. The frequency is 9. And the stem is 60. So we are having 65, 66, 67, 67, 68, 68, 68, 68, 68, 69. The same thing all over like that. Does it make sense? That is why someone can carry biro and write the value for the number. I think the sample size is around 150. So for this one now, I don't know what I know. I don't know, is it up to 150? But if you write it down, give you, I think it's 150. If you write all those values, you write them down, it gives you perfectly. I don't think it's up to 150, but you can write all the value down. That is what it's not to 150. Because you add all this together, but you can write all the value out. That is the beauty of stem and leaf. I think it's very clear. So the next one is box and whisker. It's still the same continuous variable. You can use any of them to present. No, box and whisker. In box and whisker, you have box, you have a line in the middle of the box, you have the whisker above and below. The box, the middle of the lower part of the box is the, well, we have not talked about the way you summarize quantitative variable anyway. This is just the way we present. Because in the way, if you arrange your value according in ascending order, so the position, the one in position 25%, 25th position, that is, even if they are 400, you know the frequency you express as percentage. That's what we say. The one in position 25% is the lower part of that box. The one in position 75% is the upper part. The one in position 50% is the middle. So the lower part of the whisker is the highest value in that data set. The upper part of the whisker is the lower part of the whisker is the lower value for the distribution, while the upper part is the upper value. So actually, sometimes when we run analysis, maybe we are doing practicals by running analysis, how to use, especially how to explore data. We know usually a lot of talk around it usually come. But that's just it. So later we'll talk about that upper quarter, lower quarter. Just know this. Now, the frequency polygon, if you look at this graph now, it's like the histogram. But if you now, in the histogram, if you join the middle part of each of the bar and now draw a line, that is the frequency polygon. So can you see now? Frequency polygon. So normally in a large data set, it will look as if it's smooth. In a large data set, it will look smooth. But joining the middle of it looks smooth. That's what we call frequency polygon. So it's just the histogram where you join the middle value of the histogram, give you frequency polygon. And the last one is cumulative frequency polygon, or what we call OGAI. You will notice that when we talk about this distribution, we talk about frequency distribution, relative frequency distribution, cumulative frequency distribution, and cumulative relative frequency distribution. And I told you for the cumulative aspect, instead of you to be giving the value for each outcome, or for each value, to give the frequency rather for each value, you begin to add the frequency to the total of the previous one, so that instead of it going down, it goes up. That's what happened here. You see now, when you are adding one to the subsequent one, it will never go down now, because the new one will be higher than the previous one. So the graph will begin to go up. So, and it gives you this sigma shape. This is what we call cumulative frequency polygon. That where we say at least, I told you that you use for at least or at most this frequency polygon. And by the time we talk more about normal distribution, you'll be able to understand different aspects of it also. Now, that is the way to show, to present distribution in the graph. And maybe let's just talk before we close for today, because the next thing is to how do you summarize data? So we talk about how we summarize qualitative data. Then the next lecture we discuss how we summarize quantitative data, because that one is lengthier. So let's quickly discuss, because we have already know the simplest way to categorize our variables are numerical and categorical, or quantitative or qualitative. So is the quantitative are called numerical, the qualitative categorical. We are ready to all those who are nominal, ordinal, they are qualitative or categorical. Where we have the continuous or numerical, where the one that has for the discrete, and if you use the first classification and continuous, they are quantitative. Let's talk about the qualitative. How do we summarize those data that originally they don't have value, numerical value? It's either categories, qualities like sex, male, female, ethnicity, also Igbo, Yoruba. So how do we summarize that type of data? Because naturally their values are not numbered. Now, this is just the picture, the summary of how you summarize qualitative data. Now, because you know that the values are not numbered, they are just and they are manageable possible value. Like sex now, it's only 2 possible, either male or female. All you need to do is that what is the total sample size? 400. Count how many are male, how many are female. So by saying how many are male, okay, that if we are dealing with 400 people and 250 are female, say 250 over 400 times 100%, give you the percentage. You say 150 over 400 times 100, it give you percentage. You have summarized it. But that's just simple. So now, if you look at the logic now, you can't how many are in this category. You have to do some division over. That's what we call ratio. When you are comparing two quantities of the same unit. So generally, how somebody is making a, please mute. How you summarize categorical variable is generally through ratio. So somebody is disturbing the class. Please, let's move through ratio. Let's move, please. Through ratio. And this ratio, what it means, if you remember your physics, ratio is what you get by dividing two quantities of the same unit. So the quantity we call variable. Please, let's try and mute. Everybody should try and mute. Check, please mute yourself. I don't want yes. So now, when you have two quantities of the same unit and you divide it, it gives you ratio. It's dimensionless. Let me explain the crudest way for you to understand. If a car travels 400 kilometers in 4 hours, we say, oh, what is the speed or velocity, depending on which one? We now say the speed is 400 kilometers divided by 4 hours. And when we divide 400 by 4, it gives you 100. We now call it 100 kilometers per hour. That's not a ratio, because it's still carry unit, because the numerator is a quantity, which is distance. It's different from denominator, which is time. So it's not ratio. You get speed or velocity. But if you say somebody travel 400 kilometers, another car travel 100 kilometers, you are comparing the two. You say divide 400 kilometers by 100 kilometers. It gives you 4. But it's not 4 kilometers, because kilometer cancel kilometer. Because we have kilometer as numerator, it's also cancelled the kilometer at the denominator. We just have 4. It's not 4 kilometers. Therefore, that has no unit is ratio. That's the logic behind ratio. Ratio, we are going to encounter ratio by the time we go to this score, all of them are ratio. You get to correlation, all of them are ratio, because somehow division has come to play. And in that division, you have divided two things that have the same unit. So whatever you have is dimensionless. So can you imagine now, when we say we have 400 people, we have 200 200 over 400, 200 human being over 400 human being. What you're going to get will be ratio, because you cannot say so human being again, because human being are human being. That's the logic behind it. So when you are dividing the number by this number, a number of people by this number of people, whatever you have is ratio. So logically, all of them are ratio, but this ratio will come in 3 ways. They come in 3 ways. The crudest one is what we call it ratio, the way it is. For example, when you have 500 people, out of the 500 people, you have 300 female and 200 male. You now say female-male ratio. You say 300 over 200. It gives you 3 to 2, ratio 3 to 2. Or if you call it male-female ratio, mean 200 to 300, it gives you 2 to 3, ratio 2 to 3. Can you see now? By dividing male-female, you now see here that because we are dealing with 500 people, we have 300 female, 200 male. Those 300 female, they are not part of the 200 male. They are different. We have 300 female divided by 200 male. Both numerator and denominator, they are not the same people. It's a ratio. Please, somebody is making. Let's tell you, Made, please help us move. Yeah, thank you. Now, you will now see that 300 female divided by 200 male give you ratio 3 to 2. In that situation, we have already know that male and female, they are human beings. So you cannot say ratio 3 to 2 human being. No, it's just ratio 2 to 2. But here, why we still call it ratio in the raw form is that those 300 that serve as numerator, they are different. They are not the same people as the 200 that serve as denominator. Even if you say ratio, male-female ratio, where you say 200 over 300, making ratio 2 to 3, the numerator are different from the denominator. But there are some situations where numerator will be part of denominator. In a situation where you want to know, out of these 500 people, what proportion are female? You now say 300 out of 500. You know that 300 as numerator divided by 500. Out of the 500, those 300 female are still part of the 500. Because it's 300 female plus 200 male that make up 500. You now say 300 divided by 500. Because these 300, they are still part of the 500 that are denominator. In that situation, the numerator is part of the denominator. It's a special form of ratio that is called proportion. And the proportion, we either express it as, when you say numerator is part of the denominator, it shows that the denominator is bigger than numerator. In that situation, when you are dividing it, has to give it 0 point something. Because, okay, 300 over 500. 500 goes to 300, it's 0. Until you begin to shift decimal and begin to add some 0 before you can say, okay, it's 0.6. The answer will be 0.6. That is 0.6 now. That you are divided 300 by 500, which is 3 over 2. Give you 0.6. 3 over 5, rather. 3 over 5. It gives you 0.6. Now, that is 0.6. You can leave it there. That is decimal. You express as decimal. But, most people that are decision makers, they don't understand. Imagine now, what are we looking at? Your governor said, what are we are looking at 0.6. You will not understand. But if you say we are looking at 60%. So if you now say 300 over 500 times 100, you express it as percentage, it gives you 60%. So people understand 60%. You understand? Oh, out of 100, 60. Just like say out of 10, 6. So in that situation, you express your proportion as decimal or percentage. But it's easier to express as percentage because people get to understand more. And that's why we usually express all those things in relative frequency, we express as percentage. And that's what we do actually in relative frequency, because out of the total is the sample size. For each of the value of the frequency, we put over the total expressed by, instead of expressed as decimal, we express as percentage. That is relative frequency. That is proportion we use. That relative frequency is a form of ratio, that is where numerator is part of denominator, which is proportion, which can be expressed as decimal or percentage. So that's why so many people will see the percentage of people, the women that are going to antenatal and receive LLIN is 60%. How can you say percentage is 60%? Percentage is, so you can say the proportion is 60%. Is the proportion you are expressing as either decimal or percentage? See, the proportion is 60%. Unless if you want to say the percentage is 60, it makes sense. If you say percentage is 60, the percentage of women that attend antenatal that receive LLIN or that receive IPT2 is 60. You have already said percentage is 60. But if you want to say 60%, you just say the proportion is 60%. Because if you say the proportion is 60, you are wrong, because the proportion can be expressed as decimal or as percentage. Does it make sense? So now, that's a special form of ratio. There's this special form of proportion also, where you can also include time in the denominator. Now, including time in the denominator doesn't mean that it doesn't change the calculation anyway. What it means that, you know, when there's your calculation, the data is gathered over a period of time. When it is a period of time, we express as rate. We call it rate. When the proportion time is included. For example, now, all our statistics, all this infant mortality ratio, maternal mortality, infant mortality rate, rather, maternal mortality rate or ratio, or underfant mortality rate, we express them, we use, because you gather over 1 year, is data collected over 1 year. Because you collect over, we use data collected over 1 year, we now call it rate. It's not something that just happened, maybe what we collected in June that we can, no. We can, unlike media population that we collect in June, end of June, then, but this one now, this data that we collected over a year, we use to calculate, it's a rate, because time is included. But time being included does not change anything about the calculation. It's the same proportion, the way you calculate the proportion, but because time is there, it's something collected over time, we call it rate. Can you see now? So ratio, all of them are ratio, but the crudest form is the one ratio, numerator is not part of the denominator. But when numerator is part of the denominator, it becomes proportion. And when time is included in the proportion, it becomes rate. Can you see now? So that shows that both rate and proportion, numerator is part of the denominator. Does it make sense? And that is why, especially in public health, well, in many, we are not like public health again, because we discovered that there's nothing that doesn't even public health. You can, these are the day of community ophthalmology, community, what O&G, everything, community. So public health has infiltrated everything. You know, everything we are doing now, we try to look at community, we look at individual and population together, even in all the clinical setting. Because of that, you need to understand some concepts. For example, now, how do you differentiate between, look at example, I give an example of ratio here. Maternal mortality ratio. Compare with maternal mortality rate. Maternal mortality ratio, you say the numerator is number of deaths among women due to pregnancy or birth over total number of live births. Can you see? That denominator is children given a birth alive. So the numerator number of women that die, they are different from the children born alive. So that is why they call it ratio. But all of them are ratio, but the ratio is the crudest. But when we say maternal mortality rate, when the numerator will be number of women that die due to pregnancy or childbirth over the total number of women in reproductive age group. In our own country, we use 50 to 49. Can you see now? You will now know that the number of women that die, which serve as numerator, they are also part of the number of women in reproductive age group. That is why it is proportion. But because it's originally calculated over a period of time, 1 year, that's why I now call it maternal mortality rate. Does it make sense now? So that is how to differentiate between maternal mortality rate, ratio, and rate. Many people, even some public care price, they don't understand. And most of people that are working with the relation, working with the user, they don't even understand the concept. They cannot differentiate between, and it's very, very good. And those are the things we hammer, even undergraduate students. We hammer into them. This is the difference between maternal mortality ratio and maternal mortality rate. I think we stop here, and because if we are to start this discussion on how to summarize quantitative, that one will take us longer time. You'll be tired before we finish because major part of the lecture is on that, because that one is a lot of issues are involved in that one. So we try to finish that one in the next lecture. And mind you, out of these 3 forms of ratios, because of them are actually ratios, the commonest one is the proportion. Is the commonest one. So most of the time, when you express something, you do your study, you tabulate your table, you put percentage, you are using proportion. You see that is the numerator is part of the denominator. As you can see now, because the denominator will always be sample size, the total, and number in each of the maybe category, how many are female, it has to be over the total. So numerator is always part of the denominator. So the commonest one is proportion, while sometimes we use rate. It's rare for people to even use ratio. If sometimes say, oh, male-female ratio is this, that's when we use this ratio in its crudest sense. So any question or any clarification? Any question? No question is very straightforward. Because if there's no question, you say that it's very confusing or it's very straightforward. So if you don't want to ask question by talking, you can chat. So if there's no question, thank you for everybody.